Okay, so we're going to talk about colligative properties. And what are colligative properties? These are properties that are associated with the number of solute particles and not what they are. So you can have the same colligative properties with a sucrose solution, a sugar solution, if you have the same number of solute particles as you do with a table salt solution. Okay, so what are the colligative properties we're going to talk about today? It's going to be boiling point elevation, melting point depression, and osmosis. Okay, so let's take a look at the first one. So when we look at vapor pressure, what we're talking about is that when we have a pure substance, when it's in a liquid, basically some of these liquid particles will go into the gas state. And under equilibrium, where this is a closed system, then at some it's going to reach equilibrium where those particles going into the gas state will be equal to the rate of those particles in the gas state becoming a liquid state. And that is what we now term vapor pressure. Now, when I have solutes in a solution in my liquid here, then what's happening is that these solutes also take some of the area at the surface. So I have less surface area for which my solvent particles can go into the gas state. So just by the introduction of a solute, now I have lowered my vapor pressure. Now remember, boiling point, okay, so that's what happens when we do the vapor pressure lowering. But remember, with boiling point, the definition for boiling point is that the vapor pressure must be equal to the atmospheric pressure. And it's at that temperature that my solvent or my solution will boil. Because I've lowered the vapor pressure, I need to increase my temperature in order to reach my atmospheric pressure. So if I'm looking at normal boiling point, what that means then is I have to increase my temperature in order to get my vapor pressure to be equal to 1 atmosphere. Hence, what we call boiling point elevation. Okay, so here again, the solute presence lowers the vapor pressure, and then we get, basically, we have to increase our temperature in order to have the vapor pressure equal to my outside pressure. All right, so what do we use this? Is this a practical use? And the answer is yes. So let's take a look at the effect of antifreeze on the boiling point. Okay, so here, let's just take a look at a system pressure of 0 psi. So there's no difference, it's 1 atmosphere. Okay, the pounds per square inch is like how much higher my pressure is. So when you, I apologize, the chart that I have is going to be in degrees Fahrenheit. So you have just pure water, then the boiling point is going to be 212 degrees Fahrenheit or 100 degrees Celsius. But now if I have antifreeze in my solution, so now it's a mixture, it's a solution of water and antifreeze. And basically 33%, okay, of that solution will be antifreeze. I raise my boiling point of the solution up to 220 degrees Fahrenheit. If I increase the amount of antifreeze to my solution, I can now get it to 224 degrees Fahrenheit. So what effect does this have? So when we take a look at something like a 50% solution, okay, if 50% of that solution is water, 50% is antifreeze, I've increased my boiling point to 226 degrees Fahrenheit. If I increase my temperature by having the cap on, so in my radiator system is not at 1 atmosphere, but it's slightly higher than 1 atmosphere. Look at this. The boiling point of my antifreeze mixture, the 50%, is 259 degrees Fahrenheit. But the key is this. The key is that if you compare plain water at any of these pressures to the 50% solution, where it's 50% water, 50% antifreeze, at all points, of course, the solution has a higher boiling point. Now, what effect does this have practically? Well, then if we're driving our car up the hill, like on the 5 on the Grapevine, we are less likely to have our engine boil over if we have antifreeze in our radiator system versus just plain water. And that's part of this, why colligative properties are so important, is we use them all the time. Now, what would happen if you were boiling water, okay, to make pasta? Oftentimes when we try to make pasta, we're going to add a little bit of salt and a little bit of oil to our water before we boil it and subsequently add our pasta to it. So why do we do this besides flavoring? Well, it turns out that if you had just pure water at sea level, it would boil at 100 degrees Celsius. But by adding our salt and our oil, it doesn't boil immediately. It'll boil at a higher temperature than 100 degrees Celsius because I'm adding solute to it. So that helps us to cook our pasta. Now, what you can do is if you had pure water that was boiling, you add a little bit of salt, it stops boiling, and then you have to wait a little while before it starts boiling again. It's not because the salt itself is absorbing that much heat, but it's because we are creating a solution and we therefore have boiling point elevation. And that's what we're actually doing when we add salt to our water, cooking pasta. Now, what about the opposite? What about when we try to cool and freeze a pure liquid? So when we cool and freeze a pure liquid, what we're doing is that all those liquid particles, the molecules in our liquid, okay, are organizing itself. So when it crystallizes, it's forming a 3D repeating pattern in the solid. So when you're freezing a liquid, okay, a pure solvent, and what's happening is you're getting it colder and colder until those intramolecular attractions are strong enough to override the kinetic energy. From a higher temperature, we have a higher kinetic energy. When we decrease the temperature, we're decreasing the kinetic energy, and now those crystals are going to settle down, and then those intermolecular attractions are going to take place. And that's how we get our crystal. Now, when we have solutes in there, the solutes will interfere with the formation of that 3D geometric pattern. So for my solution, because I'm solvent and solute, because you have all these little solutes that are interfering, I need to become colder, less energetic, so I can overcome the effects of the solute on the crystallization process. And that's why we get freezing point depression. So for example, when you're looking at just your pure solvent, you have all these interactions, like with water, between my hydrogen and my oxygens. But when I introduce my solute, these little green particles, they're solute, what will happen is that it interferes with the intramolecular attractions here. And so it's harder for my water to organize to form my crystal. So we get freezing point depression. It needs to be colder in order for it to organize, because then it's going to be so cold, it won't have enough kinetic energy that it won't be able to move around the solute and can just start becoming a solid. So what we get for adding a solute to my solvent in a solution, I get freezing point depression. So where is this used? Basically, freezing point depression, if you go to a place that has lots of snow and you form ice on the streets and the asphalt, you'll see a lot of trucks combine. They put sand and they put salt on the ice, and the salt will melt the ice because I've depressed the freezing point. So if I'm at, let's say, 0 degrees Celsius, pure water will freeze. So you'll get your snowfall. But now if I add salt, basically it's going to be, let's say, -4 degrees Celsius. So what happens here is that the ice will melt. It will actually take heat from the surroundings and melt the ice because you're not at the temperature for freezing. And this also, we use that to melt ice on the roads, but we also use it to make ice cream, because ice cream, if you have pure ice, that will be at 0 degrees Celsius. So you put your ice cream mixture in your ice, but what you do is you mix it with rock salt. And so as the ice and the rock, now you're forming a solution. Now the ice is going to melt. But when it melts, remember, melt is an endothermic process. It needs to absorb heat to do that. So where is it going to get the heat? It gets the heat from your ice cream mixture. That is why your ice cream mixture then starts crystallizing and becoming a solid. And that's how we make ice cream, using the same process of freezing point depression. The last colligative property we're going to talk about is called osmosis. Turns out with osmosis, if I have a solution here, and on one side I have pure solvent, and the other side I have a solution, then with these larger solute particles, I have to separate the two with what we call a semi-permeable membrane. And this allows some particles, the smaller ones, to pass through it, but not the larger ones. Well, if this has a concentration and this doesn't, what your system wants to do is to move water across to try to dilute this solution as much as possible. It wants to be close to being equal in terms of concentration. And we can discuss this, like if you mix like concentrated high C and you mix it with water, if you just put the two together and you don't stir it, at some point, the water side, the top of it, let's say you have water, it will start to taste like high C or Hawaiian punch mixture because it's beginning to mix, okay? You want to increase your mixing. It wants to have equal concentrations on both sides. The semi-permeable membrane doesn't allow that to happen. It prevents your solute from going in to your pure solvent. But what will happen is your solvent will go into your solution side and it rises up. But at the point where it stops, you measure that pressure. This difference here is called osmotic pressure. It's because of that difference in concentrations in your solution. Okay, so we can measure osmotic pressure because it's a colligative property. Now, when we take a look at osmotic pressure, then this is the opposite of trying to obtain fresh water, right? So you get your concentrated solution. We try to basically get it to the point where it's as dilute as possible. And then why does it stop? Why doesn't it continue till the side is empty? It's because we've got gravity pulling down on this mass of solution here. So osmotic pressure is going to be, and we have outside pressure here. So osmotic pressure pushing up, it stops because it's equal to the pressure pushing down on it. Now what happens is sometimes when you buy water, bottled water at the grocery store, it will say it was purified by reverse osmosis. So what happens is we actually have to do a system. We have to do work. We push down, like with a little plunger, push down on my solution. My solutes can't pass through my semi-permeable membrane, but by pushing down on it, I'm only thing that's allowed to pass through this semi-permeable membrane will be fresh water. So we actually collect in reverse osmosis. We collect the left-hand side and continue to push down, and then we'll have a highly concentrated solution here. But typically, if you just let it go and you don't do work on it, the solvent will move to the solution side to dilute it as much as possible.